Hello everyone. In this video, we will study invertibility of linear vector fields. Let me start by recalling the facts about the general function. You see, a function goes from its domain to its codomain. So domain here, let me write from domain to range. There is a technicality there I don't want to deal at this point. So we know that a function goes from its domain to its range. Now we want to figure out when there is a recipe or there's a formula which reverses this process. So it goes backward, and when we combine these two functions, they basically cancel each other. We return back what we started with. And especially when we are working with functions, so when function goes from R to R, we saw that to have f inverse from the range to the domain of the function, we need the function to be 1 to 1. So must be 1 to 1. So maybe you remember this 1 to 1 condition with the fact that, so I can draw two examples here with the fact that every value of y in the range is taken only once. And the test we had for this is called horizontal test. For every value y, there is only one value x that function gets. Well, versus to the function which is not 1 to 1, you may have some values of y which is taken by more than one values of x by this function. In other words, the function mapped more than one value of x to that value y. So this is not 1 to 1, this is 1 to 1. So that was one of the important things. If a function is 1 to 1, then you can find f inverse from its range to its domain. So if f is 1 to 1, then f inverse from the range of f to domain exists. Well, this is the general theory for all the function, for any sets that you have. Specifically, we deal with this issue in calculus, sine inverse, tan inverse, all those things where we found one-to-oneness domain, and then we were able to define the inverse. Now, the question that we want to study is, what about linear vector fields? Can be determined when they are invertible or not. There is one issue that you have to see. Linear vector fields go from Rn to Rn. Unless it is from R to R, you cannot draw the graph and figure out the horizontal line test. It's not possible. Instead of that, we will develop a theory that will tell you when such function is invertible. So we are going to try to work with matrices for vector fields of this form, where A is a matrix. So when n is equal to 1, so in that case, well, I'm going to have only one number, and the matrix will be just a constant A. So when such function AX is invertible. If A, which is basically, this is line. If you draw the graph of this guy, you notice that it's a line. And if A is not equal to 0, it will be something like that. Some function with non-zero slope, some line passing through the origin with non-zero slope. And you notice that, oh, you see every value is taken only once. So that means that for A not equal to 0, this is invertible. However, when A is equal to 0, so you draw the graph again, A equal to 0 turns this function to constant function, which is just y equal to 0. And in that case, if you draw horizontal line, you notice that there are infinitely many values that are mapped to the origin, to the 0. And that means that it's not one-to-one, and as a result, this is not invertible. We want to develop such a thing when n is bigger than 1. How about n equal to 2, n equal to 3? The first step here is to see this interesting fact that says you don't need to check all the values. A linear vector field is invertible if and only if the only value mapped to the origin is the 0 vector. You don't need to go check all the one-to-oneness in all the values. The only thing you need to check is, as a result, we have the recipe. If there is a non-zero vector v which is mapped to the origin, so AV is equal to 0, is mapped to the origin, then the linear vector field fx equal to ax is not invertible. That's how we check. We don't need to be worried about horizontal line, checking all the values. We only need to check what values are mapped to 0, what vectors are mapped to the origin. And usually that turns out to be solving a system of linear equations. Let's see this in this example. Determine if the linear vector field, so here this is our linear vector field, this is A times X, is invertible. Why do I have two of them? Okay, I'll just get rid of that one. So what we do, so the question that you have to ask yourself is this: is there a non-zero vector that is mapped to the origin by the function, the vector field f? That's the question we have to answer. So map to the origin means what? So are we going to have fx equal to 0, which is x is non-zero? So let's see what are the x's that is mapped to 0. It means that you have to find all the values of vectors such that this is true. But this, I know how to deal with this. This is matrix multiplication. I multiply that to that, so it's x plus 2y. It must be equal to 0. The second component is 3x plus 4y, must be equal to 0. Now I have to solve this system of linear equation. This is an easy linear equation because if I multiply the first row by -3 and add it to the second equation. So the first equation you multiply by -3, we are not changing anything. Adding to the second one, we get 0x plus or minus 2y equals to 0. And this means that -2y is equal to 0. And that means that the second component of such vector must be equal to 0. Now, plug it into any of these two given equations. Here it will be 3x plus 4 times 0 must be equal to 0. That means that 3x is equal to 0. And that implies that, oh, the first component must be 0 as well. So what we showed here is that x equal to 0, 0 is the only vector mapped to the origin by the function f. As a result, we can conclude that f is invertible. So everything boils down to solving this equation, ax equal to 0. And you solve it and see if there is always you're going to get 0, 0 as a solution there because origin is going to be mapped to origin all the time. But is there anything else that is mapped to the origin? That's the answer. Here in this case, there is nothing else, so that means that f is invertible. Well, if you're happy with this method, you have to be aware that if we go to R3, this will be more difficult because then you have to solve a system with 3 equations, 3 variables. And it's going to be awful. Solving those equations is not easy. Well, it's not very difficult, but it will take time. So we need a little bit more advanced machinery, and that is what this theorem is going to give us. It says there is a magical number that you have to check. A linear vector field fx is ax is invertible. I want to make it simple so that I can check not only for R2 case but R3 for Rn even, and that is given by this simple magical number, and you know that magical number, that's determinant. Find the determinant of the matrix. If it is 0, then that matrix, that linear vector field is not invertible. If it is non-zero, it is invertible. Well, back to our example up there. To check the invertibility of that matrix, the only thing we needed to find is determinant of the coefficient matrix, which in this case is, well, this is 2 by 2, so 1 times 4 minus 2 times 3, this is -2. -2 is not 0. As a result, the function, the vector field, linear vector field ax is invertible. So these are 2 things that you have to know, 2 facts. One given by this here, that invertibility is basically you're trying to check what is mapped to 0 in the case of linear vector fields. And the second thing that you have to know is that invertibility can be determined by knowing what is the determinant of the coefficient matrix.